In the last chapter of the course, we're going to talk about a specific type of sequence in the series. Get series of real numbers, then eventually series of functions. We'll see how we can use that to build approximations to functions using Fourier series. Let xn be a sequence of real numbers. We can build a different sequence associated with this, the sequence of partial sums. The series associated to xn, which we denote using the sigma notation, is the sequence Sn, where S1 is x1, S2 is x1 plus x2, S3 x1 plus x2, x3, and so forth. So it's important to recognize that a series is in fact a sequence. It is the sequence of the partial sums, the terms of the original series xn. If the sequence of partial sums does converge, we say that S is the sum of the series. And we would write, but this only makes sense if the sequence of partial sums converges. If it doesn't converge, this is not a real value. The xn's, these are the terms of the series. The sn's are partial sums. If a series converges, then the terms of the series have to go to 0 when n goes to infinity. How do we show that? Well, if the series converges as a sum, let that be S, the limit of the partial sum. What can we say about the limit of the xn's? That would be the limit of the nth partial sum minus the n minus 1 partial sum. Now, we know that this limit exists here, limit of the sn's, and so we can use the theorem on the operations of limits, on limits, to say that this is going to be equal to, if you didn't know that the series converged, if you didn't know that the partial sums converged, you could not necessarily separate the limit of the sum as the sum of both of these take on the value s, so we get 0, right? Would you believe that there's a Cauchy criterion for series as well? Series xn from 1 to infinity converges if and only if for every epsilon greater than 0 you can find an epsilon integer such that the sum of the terms n plus 1, n plus 2, all the way up to m is smaller than epsilon whenever m n greater than n. Well, the proof, quite simple. This series is actually the sequence Sn of the partial sums, and if you look at Sm minus Sn, you get exactly this expression. So if Sn is Cauchy, that means that Sm minus Sn would be smaller than epsilon, assuming that we have an epsilon to start with. Whenever n is greater than n epsilon for some n epsilon, which is the same thing as saying that the sequence converges, because when you're working with real numbers, every Cauchy sequence is a convergent sequence, and hence the series is a Cauchy series if this is smaller than epsilon. This is just restating what it means for the sequence of partial sums to be a Cauchy sequence. There's nothing much here. It doesn't even deserve a QED. It's rewriting the definition. The one above did deserve a QED, and I forgot to write it in, so let's put it in. I will leave you here with the idea of the comparison tests. There are other tests that you can use to show if the series converges. You've seen some of them in your calculus course. When we talk about series of functions, you will see, because we'll describe some of the other tests. The main one here that we'll use is the comparison. Quite straightforward. If you have two series whose terms are all non-negative, if there is a point in the sequence of the terms for which the terms xn are all smaller than the corresponding terms yn after the point, after the threshold k, then the series of the xn will converge if the series of the yn converges, and the series of the yn diverges if the series of the xn diverges. Does this make sense? Well, in order for this series yn to converge, the yns have to go to 0. Now, that's not sufficient. Sometimes the yns could go to 0 without, yn converging, but here we know for a fact that yn converges. That's what we're starting. So the yns go to 0, and we know that the xn's are sandwiched between 0 and yn, so we know that they will eventually go to 0 as well. And the yns go to 0, and the partial sums that they build converge. You don't really have a choice, right? The xn's, their partial sums also have to converge. But if we've learned anything in this course, is that this argument is not actually a proof of the statement. How do we actually prove the statement? In calculus, you make a link between series and areas underneath the curve. So this is a test which is analogous to the test for convergence of improper integrals. And then your argument is that if the area below a curve goes to infinity here is finite, if I have any other curve below that one, its area also has to be finite, because it's smaller than a finite area. But we don't really have this interpretation at our disposal. So what do? What we have at our disposal is the definition of a convergent sequence. That is what we. If epsilon be some arbitrary positive value, we know that there exists an n epsilon and n such that the sum of the n plus 1 term all the way up to the nth term will be smaller than epsilon and greater than 0 whenever n greater than n epsilon. How do we know this? Well, the series yn converges, and so we use Cauchy's criterion. Cauchy's criterion had the absolute value of the sum of the terms, but here all of the terms are assumed to be non-negative, and so this sum has to be greater than or equal to 0. Now you can also choose your m to be greater than or equal to m. Worst case scenario, you relabel, you switch the labels, but it does work this way. So that's by the Cauchy criterion. Now, set m to be the maximum of the k that we had here in the statement of the theorem, the point after which all the yns dominate all the xn's, and the n epsilon, which works for the Cauchy criterion. Whenever m is greater than n is greater than this new m, and we must have that 0 is smaller than or equal to the sum of the xi's, which must be smaller than the sum of the yi's. And we know this is true because n and m are greater than k, and we have that the yns dominate in that case. And we know that this is going to be less than epsilon because m and n are greater than n epsilon by virtue of being greater than m, they're greater than both simultaneously, which means that the Cauchy criterion applies to the series xn and goes from 1 to infinity. Statement 2 is just a contrapositive of that statement. Right? If the series of yn converges, then the series of xn converges. Flip the order, negate the statements, and you have statement 2. So they're exactly the same statement, which leads to the end of the proof.